Another application of exponential functions that we often see in modeling is with radioactive decay. This is very similar to population growth when it grows at an exponential rate. It's just that the amount of radioactive material, instead of growing, is decaying at an exponential rate. The basic equation for that is Q. We generally use Q for the quantity or the amount of radioactive stuff that we have, rather than using P for population, because we're not counting people or deer or whatever. Okay, is equal to Q naught. That would be the initial amount, so that would be the quantity at time 0, e to the negative k times t. Now, as a general rule, when you have a letter standing in for a number, you can't tell by the presence or absence of a negative sign whether it's positive or negative. The convention is that in these exponential equations, k represents a positive number. Because we want this to be exponential decay, we need our exponent to be a negative multiple of t. Since the base is e and that's bigger than 1, if I'm taking e to positive powers of t, I'm getting exponential growth. If I make it negative multiples of t, I could essentially say e to the negative kt is the same as e to the negative 1 to the kt. That's like 1 over e to the kt. That's like having a base of 1 over e. Since that's between 0 and 1, that would give us exponential decay. All right, so as with the population problems, we're going to be given some information and just asked to try to find the exact equation. And that's going to mean coming up with the constants that we would plug in for Q naught and for K. Okay. I will just let you know there are several different variations on the formula for radioactive decay. Make sure you read the directions. If you're asked for something in this form, give something in this form. It's very easy to Google and come up with a formula that has 1/2 as the base instead. The reason for that is that we're often given the half-life of things. Now, the half-life is just the amount of time it takes for half of the radioactive material to decay. When we were talking about interest, we mentioned that the amount of time it would take an investment to double didn't depend on how much you invested. It's the same amount of time whether you invested $100 or $1 million. It's going to double in the same amount of time. Same thing with radioactive decay. It's going to be cut in half in the same amount of time. And we call that amount of time the half-life. Okay. So very often that's the information that's given. So I took this problem, I basically took the data from question 26, although I'm not asking quite as many questions as the book is from that. But technetium-99 has a half-life of 6 hours. That's a relatively short time. That's good because this is often used in medicine. Patients will be injected with this so that the scans can show up, but we don't want this stuff staying in our patients for too long. Okay. So it has a half-life of 6 hours, and at noon, a patient is injected with 10. This symbol means millicuries. That's the amount of stuff we put into our patient. Okay, so all I want to do is come up with a formula of this form. So I want to figure out what Q naught and what K are. Well, Q naught is 10. And we'll just be using these units of millicuries for our quantity. I'm going to be using hours as my units for time. Okay. So I now know that Q is 10 e to the negative kt. Now, I need to use this half-life information. Okay. Well, so this tells me if time were 6, the quantity would have to be half of the initial quantity. So that would be 5. So I'm going to replace Q with 5. I'm going to replace T with 6. So I can just make this negative 6K. If I divide through by the 10, that gives me 1/2 is equal to e to the negative 6K. And now I can solve for K. The natural log of 1/2 is negative 6K. That would be the natural log on this side. That's just going to be the exponent. Okay. So K would be negative the natural log of 1/2 all over 6. Okay. By the way, that will make k a positive number. So the convention, as I mentioned, is that k is positive. When we want a negative exponent, we explicitly write the sign. How do I know that that is a positive thing? Well, the bottom is obviously positive. The top is the opposite of the natural log of 1/2. But if I think about my natural log function, I know it has an x-intercept at 1, 0, because all log functions, at least prior to any transformation, do. So 1/2 would be to the left of 0, but that's where my y values are negative. So the natural log of 1/2, or anything between 0 and 1, is going to be negative. Okay, so if I were to write this formula out exactly, and I asked for it exactly and then with k rounded to 4 places. So exactly it would be q is equal to 10 e to the negative natural log of 1/2 over 6 times t, with that being my k. If I wanted to get a decimal approximation of that, let's see, negative natural log of 1/2 divided by 6. Okay, so k was negative natural log of 1/2 over 6. That's approximately 0.69314, blah, blah, blah. If I'm rounding to 4 places, that would be approximately 0.6931. So I would say q is 10 e to the negative 0.6931 t. Okay. Again, to get to this, I need a calculator. This is where you would leave things on an exam. Ordinarily, when I have 2 negatives, I would simplify those, but I was asked to get it in this form where there's a negative sign in front of my k. Okay. All right, excellent. So that gives us an example of radioactive decay. In the next video, I'm going to give you one to work on. In this case, we were given the half-life. In some of the homework, you'll be asked to actually find the half-life. So we'll practice that in the next one.